Hi everyone. In this video I am going to tell you about IC parallel adders. IC parallel adders. In the previous video I have explained you about parallel adders and parallel subtractors. So subtraction can also be done using addition only. So that's why parallel adders are very important for both addition and as well as subtraction. Here parallel adder means we are having a 4-bit parallel adder which is an IC that can be generally used for multiple purposes and can be extended for more than 4 bits. Okay, if you want to go for 8-bit parallel adders, then we are using 4 two 4-bit adders, two 4-bit parallel adders. Okay, several ICs are available. Among them, 74LS83. 74LS83. This is the most commonly used IC, which is a TTL logic family, which is having a TTL logic family. LS stands for low power Schottky. LS stands for it is a low power Schottky. So low power Schottky, it is a TTL logic family. So 74LS83, it is the IC number of 4-bit parallel adder. It is the IC number of 4-bit parallel adder. 4-bit parallel adder. So other than this, we are also having few other ICs. There are several ICs available. They are 7483A, 74LS83A, and 74283, 74283, and 74LS283, 74LS283. All these are TTL families. All these are TTL logic families. Okay, so we are having several logic families like TTL, DTL, RTL, CMOS logic families. Okay, TTL we are using for fastest logic family. We can say TTL is the transistor logic family, which is used for the fastest operations. Okay, these four are commonly used. Among them, most commonly used one is the 74LS283, 74LS83, 74LS83 AR 74LS83, which is a 4-bit parallel adder. Which is a 4-bit parallel adder. Now I will draw the IC diagram of this 74LS83. This is 4-bit parallel adder, that is 74LS83. It is having, as you are having 4-bit parallel adder, input carry C0 and input bits A0, A1, A2, A3, and you can write here only B0, B1, B2, B3. Okay, so B3, B2, B1, B0, and 4 outputs as S0, S1, S2, S3. So okay, these are the 4 inputs A0 to A3, and these are another 4 inputs because addition can be done between two 4-bit numbers. Between two 4-bit numbers. So A0 to A3, this is one 4-bit number, and B0 to B3, this is another 4-bit number. So these two 4-bit numbers are added and produces a sum S0 to S3 along with a carry. So that carry is shown here C4. Okay, this is performing a 4-bit parallel adder. Suppose I want to go for 8-bit parallel adder. How to implement 8-bit parallel adder using this 4-bit parallel adder? So that is done by using cascading of parallel adders. Cascading IC parallel adders. IC parallel adders. In the previous videos, I told you first 4-bit parallel adder. Later, I have I shown you the delay which is there in the 4-bit parallel adder, nothing but ripple carry adder. As the carry is being propagated from one stage to another stage, as the number of stages increases, the delay also increases. So that's why we have already seen a look ahead carry adder, which is used to reduce the delay, and it is used to generate the carries in the beginning itself. So such type of amendment is there in this particular 4-bit parallel ladder 74LS83. So 74LS83 consisting of look ahead carry generator, such that it does not have any delay like your ripple carry adder. So that is also another important point I will write here. It consists of look ahead carry generator, look ahead carry generator to avoid delay in the addition. Okay, so this 4-bit parallel ladder 74LS83 is provided with the look ahead carry generator, which is a 4-bit look ahead carry generator. So whenever the inputs A and B are available, automatically the carries are generated by using carry generate and carry propagator. So A, B and C input. These three are sufficient to generate carries for the next stages. Automatically the sum also produces at fast compared to the normal ripple carry adder. So coming to the cascading of ICs, when we are using 8-bit adders, so for 8-bit adders, we should use two 4-bit parallel adders. Okay, so for 8-bit adders, if you want to do addition between two numbers like A and B are the two numbers which are 8-bit numbers. 8-bit numbers are nothing but which are having A7, A6, A5, A4, A3, A2, A1, A0, and similarly second number B7, B6, B5, B4, B3, B2, B1 and B0. When you are adding these two, see the first 4 bits are applied to first 4-bit full adder, so first IC1, and the second 4-bit numbers are applied to second IC, that is IC2. So IC1 is applied with A0 to A3, B0 to B3, and IC2 is applied with A4 to A7 and B4 to B7. Okay, this is okay. But what about the carry generated? Okay, we are having a carry here in this IC. We are having a carry input and as well as carry output. Because when we are using 4-bit parallel addition, we have input carry for the full adder, and as well as after the addition, we will be having a carry generated at the output. So here the input carry, of course, we are giving, that is initially the input carry is 0. If any carry is generated at this last stage like C4, this carry will be the input for the second IC. This carry will be input for the second IC. Suppose just a rough diagram I am drawing here. Just 8-bit parallel adder using two 4-bit parallel adders. So this is A0 to A4, A0, A1, A2, A3, and this is B3, B2, B1 and B0, and the sum which is generated from this first IC, this is IC1, 74LS83, and the carry initially it is 0 here. Okay, and now we are having one more IC, one more IC. Okay, this IC2 is having inputs like A7, A6, A5 and A4, and similarly we are having here B7, B6, B5, B4. Okay, now we are having here it is some S0, S1, S2, S3, and thereafter we are having the sum output S4, S5, S6, S7, and now this carry is the input that is coming from this output carry. Okay, the input is the carry here. So this is the carry that is generated. Let us consider this is the carry C4 and this C4 is connected here. Okay, and this carry is the next stage carry. Let it be C8. Okay, so this C8. So what is the result now after this addition? The result is, so final result is C8, S7, S C8, S7, S6, S5, S4, S3, S2, S1, S0. Okay, so S0 to S7 and along with the carry C8. Okay, so this is the way of using IC parallel adder IC74LS83 in cascaded form. Cascaded form is nothing but one output is connected to the next input. One output is connected to the next input. Here the output of the carry from the first IC is connected to the input of next carry Cin. Okay, so in the using with this knowledge, in the next video I will explain about the BCD adder, so that the BCD adder can be implemented with this IC. See, everywhere in the XS3 also we are going to use this 74LS83. So this 74LS83 has a significance in BCD adder, XS3 adder, and as well as it's a subtractor. Okay, thank you.